Hey, so we'll get started. For those of you who don't know me, I'm Angus. I'm one of the tutors for this subject. I take two of the labs. Today's lecture, because it's Flex Week, there'll be no new content. So instead, it'll be revision. The format of this is we're going to start by going over the context 2 problems, and some revision essentially, so DP on trees, and also just some assorted problems covering a wide variety of the technique that's been covered so far this term. Then, depending on time, might go over some off-syllabus stuff for interest. Obviously, this stuff cannot appear on the exam. You don't have to worry about it. It's just there for interest. I'm not sure how much time we'll have for that. It really depends how long it takes us to get through the revision. I guess we'll get started on the contest 2 problems. So we'll just go over them in order, A, B, and then C. So for A, for those of you who don't remember the problem, hopefully you do. It was just over the weekend. But there's n+1 towns joined by n trains. Each train has a duration it takes to go between the two stations, and also leaves every b hours from time 0. So the train leaves at time b, time 2b, etc. You want to maximize the minimum time spent waiting at any town while still arriving at the final town by time t. So you have like, yeah, time limit you want to get to the end by, you want to maximize the minimum time spent waiting. So yeah, the input format, you're given n number of towns up to 100,000. You're given t, that is the time you have to get to the end, and then the input. Hopefully you'll remember that from the contest. Output, most hours you can spend at each town. Okay, so I guess, yeah, it's not obvious how to immediately tackle it. Like there's not, I guess, simple greedy, whatever, for tackling the problem on its own. However, hopefully you notice the phrase maximize the minimum. This is kind of one of the phrases we told you to look out for. Even if it's not in there explicitly, like the phrase maximize the minimum. In the problem, you want to, maximize the minimum time spent at a town. Because of that, you might want to think about using binary search. Yeah, as Ravine said, several students tried DP. It didn't work. Obviously, like you're not necessarily going to get the correct approach straight away. Like it's normal to try and tackle a problem and get stuck for a bit. But yeah, when solving this problem, the key was to think about using binary search. I guess check monotonicity. Let f of x be true if a waiting time of x is feasible, and 0 if it's not. Well, if you can wait a minimum of like 10 minutes in every place, that implies you can wait 9 minutes, because you can wait for 10 minutes, or waiting for 9 minutes is like included in waiting for 10 minutes. So the function of can we wait at least x minutes at every station or city is a monotonic function, which means if we have a way of checking it, then we can apply our binary search. Then the thing to think about when tackling binary search problems is a decision problem. Is checking can we wait at least X minutes at every station, is it easier? Because it isn't always easier, but in this case, well, it is. You just essentially just try greedy. Because if we want to wait at least X minutes at every station, so we're checking can we wait X minutes, then we might as well wait X minutes at the first station and then catch the first train after that. So the train leaves at X plus 1 minutes, for example, and that's the first train to leave after X minutes. We might as well take it, because we want to like end by time t. Otherwise, well, that's kind of what I do in the problem. Get the end by time t. But we need to spend at least X minutes. So I think it's fairly obvious to see that you might as well spend X and spend as little extra time as possible. Yeah. Do it in one pass as you go through. Keep track of your current time. When you get to a station, a town, add X to correspond to waiting for X. Then you find the nearest departure time. And on the next slide, we'll go over in a bit more detail how that works. The complexity of this, assuming you can do this in order n, which we'll explain in the implementation details you can, then the answer is no larger than t. So you can do it in n log t. N for the check, n log t for the binary search. And some implementation notes. You should use long longs, or if you use ints, you need to be proactive in checking for overflow. It is possible to solve it using ints, but it's easier to solve using long longs. Because if you just keep going through and see how much time do I spend if I wait X minutes, it's possible that it'll exceed an int. And you do your check, number will be negative, and it'll be like, yeah, we can wait 3 billion minutes because 3 billion becomes negative a billion. So yeah, overflow can obviously cause bugs. So in this problem, it's better to use long longs. The question is, how do we round up P to the nearest multiple of Q? This is used because trains leave every multiple of some number. And so to find when the next train leaves, find what is the next multiple of some number. Mathematically, this is P divided by Q rounded up times Q. You can think about this like if we're after the second train leaves, so we're kind of like 2.5 or something train lengths in. So like if a train leaves every 10 minutes, and currently it's 25, we'll divide this by 10, then 2.5, round it up, get 3, and multiply by 10, and we get 3, which is the next train arriving. So yeah, mathematically, we're working out this. In C++, obviously, P divided by Q rounds down. Or at least positive integers rounds down or truncates. And so to work out this first part here, we can say, well, if Q is a factor of P, that is, if Q modulo P is 0, then the floor and ceiling are the same. And so we just do this. Otherwise, to round up, we check if the modulo is non-zero, add 1. And that's to work out this. You can multiply by Q. That's one way of doing it. Alternatively, you can directly round up by doing this. So if P mod Q is non-zero, because if P mod Q is 0, then Q is a factor of P, sorry. P is a factor of Q, and then Q is a factor of P, getting mixed up, which means we can then catch the next train immediately, like straight away. There's no need to wait for a train. We can just catch a train straight away. Otherwise, if this is non-zero, we can round up, and this is just saying, well, get P mod Q. However, like for example, if you are at 11 seconds and the train leaves every 10 seconds, then P mod Q is 1. But we need to wait 9 seconds, so 10 minus 1 is 9. And kind of see that, this is another way of doing it that doesn't involve this over here, just kind of directly rounds up. Another way of doing it is use the fact that rounding up is equivalent to minusing 1, then dividing and adding 1. These are 3 different ways of computing this, which is required in the check. Another note about the problem, some students got compile error because they declared arrays too big to fit in memory, which is quite large. Just, I guess, keep that in mind. Make sure that the arrays that you're declaring can fit in memory. This is the code for the problem. So this is our binary search check function. So we're going, okay. This is the time to get to the first station, because when we arrive, we can take the first train immediately. And then we go, okay, for each city, wait there for X seconds. This rounds up immediately. This is using the third idea, I think. Yeah, this is using the third idea where -1 divide, then add 1. Work out. Oh, writing is tough. Try again. P on Q rounded up. that's this here, and then we multiply it by this. And then we add the time it takes us to spend on that train. Finally, at the end, we just check, is that less than t? And this is just scanning the input and doing a binary search here. Any questions about the problem? I can answer them. Otherwise, I'm going to move on to the second question. So in B, there are n sizes of boxes, each one from size 1 to size n, each with some value. You know that a box of size k can carry other boxes as long as the direct contents have sizes adding up to less than k. So a box of size 10 can take one box of size 9, or one of size 5 and one of size 4, etc. But a box of size 10 can't carry two of size 5. And that's only direct content. So if those boxes have other stuff inside of them, that's perfectly fine. It's just, the immediate size of the boxes. What is the maximum value you can carry if you only carry a single box? So obviously you have boxes inside boxes. Input, you have n up to 5,000. Then you're given the values of each box up to 200,000. And output, one number, the maximum value, that is the maximum value you can carry in a single box. So the one thing to note, this is an optimization problem, and you do have the corresponding decision problem. That is, can we carry at least X dollars or whatever the unit was? We can find if we think about it. We're going to not think about it for now. But the decision problem isn't any easier, so you can't binary search. It is really easy if you thought about that when solving the problem. But obviously, after some thinking, if you find that it's not any easier, then you move on to a different technique. It's not always immediately obvious binary search, not binary search. You might think, can I binary search? Think about it for a bit. No. But yeah, an important observation, I guess, is that the box you carry at the end should be of maximum size. Because proof by contradiction, let's say you wanted to carry a box of smaller than the maximum size, and you can make this better by just putting that box inside a bigger box. And now you have a better answer. So we always want to finish up with a box of the biggest size, that is size n, and then put other boxes inside of it. The is the value of box size n, that is the value assigned to box n, plus the maximum value you can fit into n take 1 unit space, because we're going to say put these n take 1 units inside our big box, and that's our answer. We can solve this using dynamic programming. So a natural order of the states is just increasing size, because we could only put small boxes inside big boxes. So to order our states, it makes sense, order them by size. Let's just try the simplest possible state we could probably have. And that is, given k, what's the maximum value you can fit into k units of space? I guess a slightly different state, but kind of similar state, is what's the maximum you can have with a box of size k. This state is slightly different, but I guess similar. But let dpk be the maximum value you can fit in k units of space. That could be from a box of size k, or a box of size k on 2 plus another one of size k on 2, or k boxes of size 1, etc. Can we make a recurrence? Well, let's just consider the moves available. So I guess one move is to take a box of size k, and in that case, what can we put in it? Well, the best thing to put in a box of size k is whatever we can fit inside k take 1 space. That is, take a box of size k and fill its interior with the maximum value. That is dp k take 1. All these multiple boxes. But you can have a breakpoint. What that means is, if you have multiple boxes, that means there exists some j such that you have boxes adding up to j and boxes adding up to k minus j. So you can kind of split it in two and say, we're going to add these two components together for some j. If there's only one box, this won't be true, but in this case, we're considering multiple boxes. So we're guaranteed that there exists some split point or breakpoint. So then our recurrent is Option 1, take a box of size k, that is value k, and fill it with the best possible amount we can fit in k take 1 space, which is the definition of dp k take 1. That's case 1. Case 2 is take multiple boxes, and for each j from 0 to k, from 1 to k take 1, we try, okay, what's the most we can fit in j units of space, and what's the most we can fit in k take j units of space. These add to k, we have some configuration that adds to k. Across all j's, we try all configurations. So that's the dp recurrence. Complexity, well, order n states, requiring constant here, order k, that is order n here, because k is less than n. So total of n times n, order n squared. N is 5,000, n squared is 25 million. We're all good. Yeah, some implementation details. You don't need longs. There's no more than n boxes can ever fit inside. Proof by induction. Yeah, fairly simple. If you assume the box of size k can only have k boxes in it, then the box of size k plus 1 can only have k plus 1 boxes in it. This isn't required to solve the problem because there's no harm in using longs for the most part. If you're not sure, just use longs, but not required. There are alternate solutions that also use DP. One of them is to have a state with 2 parameters. For example, you fill in k units of space with boxes of size up to j. You also have a DP that has 2 times n states. There are a few ways of doing this. Left as an exercise to the reader. We'll describe one solution. The other ones are similar, but yeah, left as an exercise. One thing to keep note of, if you use this solution with n squared states, you require a 2D array to keep track of all the states. It's important to note that in C++ and C, it is faster to traverse a 2D array by rows than by columns. What I mean by that is if you have like your 2D like nested for loop, you have like from I, you have like I going from like, I don't know, 0 to n here. And then you have j going from 0 to n here. It's much faster if you access array ij in this order. It's much faster than if you access ji. The reason is because how memory is laid out. If you access it this way, you're accessing the arrays memory like in the actual order it is. In this way, it's kind of all over the place. And you'll find a significant speed difference. In this problem, potentially like 3 or 4 times speed difference. It's kind of crazy how much this like caching can actually change your speed of your code. So yeah, because of consecutive locations in memory. So keep that in mind. It's not always required when solving like 2D array problems, but if you're solving a problem and you have a 2D array, you're kind of like, why is my code saying time limit exceeded? It should be fine. Just like try swapping the array indices around. You'll be surprised at how much of a difference it can make. Just keep that in mind. So this is the code for that. It's nice and short. So this is our DP. So scan the input. And here we do exactly what we described 2 slides ago. So case 1, this is what was VK before. Now it's AI plus DP I take 1. And case 2 was find a j that splits it. Yeah, this is pretty much identical to the idea before. Then the overall answer is just a box of size n, which is the value of that box plus the most we can fit in that box. And that is our answer. Okay. If there's no questions, I'll move on to problem C. So is beakers, or scientists, I think it was called. So in the problem, you have n beakers numbered from 1 to n, all initially containing different chemicals, although each chemical is A, B, or C, acid, base, or neutral. M reactions occur. Each one involves pouring the contents from one beaker into another, and the contents combine. If the combined contents include at least one acid and at least one base, the entire mixture turns into gas, and the beaker is now empty. After all the reactions have occurred, you want to know for each initial chemical which final beaker it's in. So like if you pour one into another, then into a third one, the answer is that third beaker. Or if that chemical was turned into gas. And the input, you're given n number of beakers / chemicals, m number of mixtures up to 100,000. Then you're given n characters. That's for each chemical. Is it an acid, base, or neutral? And then you're given the m experiments. Okay. Output n lines. Each one you output the number of the beaker where the chemical finished, or 0 if it turns into gas. Hopefully that makes sense, since hopefully you read the problems. But now onto the solution. So we are merging objects, kind of. When we pour a beaker X into a beaker Y, we merge their contents, which makes it seem like maybe we could use some sort of union find. However, we can't just use standard union find to like merge the beakers. The reason is because a chemical can leave a beaker. Either when we pour a beaker X into a beaker Y, and so then X is empty, or if like it turns into gas, then they're both empty. So we can't just merge beakers together. But yeah, the key thing is that mixtures themselves never get unmerged. So even though like beakers become empty, the mixtures don't become unmixed, and so we can union find the mixtures together, but not the beakers on their own. To handle this, we can keep track of the set that a chemical is in using a union find, because we merge chemicals and never unmerge them. And then we can keep track of, for each beaker, which set is currently occupying it. Some details. If that doesn't make sense, let me know. Hopefully, with some more details, it'll make some more sense. So in our union find, we have an array which stores which set each chemical is in. This is just standard union find. So when we merge two chemicals together, we pour X into Y, we merge the chemical that was in X with the chemical that was in Y, as we would with a normal union find. On top of this, kind of the main key is that we have another array that stores, we have another array that for each set just stores if it has an acid or a base in it, because we need that detail for merging. But this is the important detail. We have another array which stores for each beaker which set currently occupies it, or if it's empty. So initially, set I, or chemical I, occupies a beaker. When we merge X into Y, then we union find the chemical in X with the chemical in Y. We make sure that beaker Y says that it has that mixture in it, and that beaker X is like, well, I'm empty now. If we do a future merge, we're merging like a non-empty thing with an empty thing. We need to keep that in mind. So yeah, when we merge two beakers, we merge the corresponding sets. By corresponding sets, I mean the set of the chemical that's in it. However, if one of those is empty, you shouldn't be merging with an empty set. Otherwise, you might cause some issues by accidentally merging everything together. Another thing to keep in mind is that we use the empty set to represent a chemical being gas. So to represent being turned into gas, we can merge a chemical with 0. That makes it easier to deal with. And in that case, obviously, we don't want to accidentally merge other things with 0. We should keep that in mind. Turn a chemical into gas by merging it with 0, as I just said. So Find complexity is the same as a standard union find. That is n log n or n inverse Ackermann n, depending on what specific method you've used. Yep. This is some code, or at least the first part of some code. It goes on to the next page. So this is our union find. So this is the representative, or like the set that a chemical is. So this is the set that chemical I is in. Here we have the type of a chemical. We're saying 0 neutral, 1 acid, 2 base. The type corresponds to a given set here. We have in beaker. This stores the set that is currently occupying a beaker. That is the chemical that's currently in a beaker, or 0 if there's no chemical in the beaker. Which beaker stores which beaker a chemical is in. This is used just to gain the answer at the end. So the question of rep I is the parent in the union find. Yeah, if you think about union find as a tree, rep I is the parent in the tree. In this case, we use path compression, which I think was covered in the union find lecture as one of the 2 ways of doing union find. So just initialize our union find. We're just saying the rep that is the parent in the union find tree, or like what set you're in is just yourself, as is the beaker you're in, and also which beaker you're in. They're all I. That's just initial values for everything. This is just path compression, which was covered in the union find lecture, which is data structures, which makes union find n log n. The proof of that is quite difficult. Here, this is merging to beaker. So by merge, I mean pouring beaker X into beaker Y. So in X, we're just find rep, that is find the root. So we're finding the root, or the set that is in beaker X and the set that is in Y. Then we check if they're both non-zero. That means if they're 0, that means there's nothing in the beaker. So we're saying if there's something in both beakers, then union find merge them. So set the parent of X to Y in the union find. Also, we're saying if there's an acid and a base, if 1 plus 2 is 3, then we're saying, okay, we're merging it with 0. We merge with 0 because that's what we said was turning into gas. So we say your parent in the union find tree is now 0. We also at the same time say in beaker Y is 0. So now we're saying there's nothing in beaker Y because it's empty. It's been turned into a gas. Two assignments on one line. So I fit it all on one slide, basically. Otherwise, we're saying put together, we're updating what type is in Y by saying consider what's in X. We use an OR here, a bitwise OR, because we say 1 is acid, 2 is base. We bitwise OR them together. It's a simple way of combining them, because like if they're both acids, then 1 or 1 is still 1. If they're both bases, 2 or 2 is still 2, or 2 or 0 is 2. So this just says get like the combined what's in both of them, and that's in Y. Second case, if there's something in beaker X but nothing in beaker Y, then we're pouring X into Y. So we say, well, now X, what was in X is now in Y. And also which beaker, which stores which beaker this set is in, this chemical is in, we now say that's in beaker Y. The other 2 cases, in both the other 2 cases where X is empty, because it's kind of 4 cases of these 2 variables in Y. Those ones don't matter because X is 0. There's nothing in beaker X, which means our merge is doing nothing. So we can kind of ignore it. And here we say in beaker X is 0. We're just saying, well, we've poured beaker X into beaker Y. So regardless of what happened, beaker X is now empty. And then some stuff is cut off, but that's just, I believe, the end of the statement. This is just the end of like the closing semicolon. All the codes on here. This is our merge function. We then say in our main, it's fairly simple. We just scan the input, update the type, based on if it's an A or a B. We then just do all the merges. Because the merge code is all here, let's call that function, and then print out which beaker, because if you remember which beaker stored which beaker a chemical was in, or 0 if it was a gas, which is exactly what we want for this problem. Okay, so that's one solution to problem C. There's also a second solution, which uses small merge. Use small merge. For each beaker, we maintain a list of all the chemicals currently in that beaker. When we merge two beakers, we insert all the elements from the smaller list into the bigger list. This is very similar to the size heuristic for union find. So if we have, let's say we know that like in beaker 1, there's 1, in beaker 2, there's 2. We merge 2 into 1. So now in beaker 1, there's 0. There's nothing in there, or like the empty set. In beaker 2, we now have like the combined mixture of 1 and 2. Assuming no chemical reaction happened, that's what happens when we pour 1 into 2. Now, let's say we pour 1 into 3. We want to combine these sets. Small merge just says the easiest way to combine these lists is to add 3 to the end of this list rather than adding 1 and 2 to this list. We still end up having 1, 2, and 3 here. We just add the smaller list to the bigger list because that's faster because we're changing lengths. And the complexity of this is n log n. A quick proof is because an element can only change lists at most n log n times, because if we, for example, put like this element 3 into this set here, we guarantee the size of the set that it's in is doubling because it's a smaller set. The other set must be at least as big as us, so we must be in total doubling. That means you can only change lists at most log n times, which is amortized n log n. The proof might be a bit might seem a bit weird, but this is pretty much the same as the size heuristic for union find. Similar idea, similar proof. And to keep track of when a beaker is turned into gas, because we have a list of everything in a current beaker, when something's turned into gas, we just iterate over that entire list and say, you're all gas now. Importantly, because each thing is turned into gas only once, this procedure is order n, part of it is order n, because each thing's turned to gas only once. So we have n log n for small merge, order n for this, we get order n overall. You can click this link to read some more about using like small merge ideas or giving explicit sets of the elements. It might be interesting. So that's the end of this discussion on contest 2. Quickly at the end, if anyone has any issues they encountered, or whether that's like a bug or difficulty seeing things, like maybe you struggle to see binary search the answer, something like that, feel free to say them now. You might learn something from common errors. So if there's an error you had that you think's worth mentioning, feel free to bring it up now. Give a bit of time to do that. Otherwise, we'll move on to some revision. But yeah, I do recommend, if you had some issue that you think I didn't bring up, share it now, because it could be of the benefit of everyone. I'll give you 30 seconds to a minute for that. Or any questions about contest 2. If you didn't understand any of the solutions. If not, okay, let's move on to some revision. So I'm going to cover DP on trees. That's pretty much exactly what the name suggests, just applying dynamic programming to trees. And there's 2 problems there. there's one easier problem and one harder problem. The harder problem is quite involved, so feel free to like ask me questions if you get lost, because yeah, there's quite a lot going on in the harder problem in that. We'll do the easier one first. We then have assorted problems. There's 3 problems here. The first 2 I think are fairly standard applications of technique. The third one is quite a lot harder again. And then once you finish those problems, we're covering some off-syllabus stuff for interest. But again, that's definitely not, you don't have to watch that if you don't want to, but feel free to. On to that, DP on trees. So I guess, yeah, what is DP on trees? Well, trees are nice because subtrees don't share vertices. It's nice for doing DPs because we know that like if we have a node, all it's kind of independent. The usefulness of this might become clearer when we start doing some problems. But kind of the nice thing is we can kind of isolate the 2 children, solve them often, solve them independently, and then do some work with the parent to merge them back together. If we have a DAG instead, it's harder because kind of children meet up, so you can't treat these 2 things as kind of independent. You can do some DPs on DAGs, finding longest path on a DAG, you can do. But stuff where overlap matters, like vertex, count how many distinct vertices it can reach. Easy on a tree. Just how many vertices are in each of my children, add them together. But on a DAG, you can't say, well, how many vertices are there on each of my children? Because it could be stuff shared. So stuff like that, yeah, is harder on a DAG. But trees are nice. And we're talking about trees now, which is nice. Yeah, and usually it doesn't hurt to assume trees are rooted. So often in tree problems, you're just given a tree, an undirected tree. However, often in DP problems, you can arbitrarily root the tree. Just say, okay, root it at 1, for example. Now all edges are directed away from 1. As we'll see, you can often just do this and it works. Again, obviously not 100% of the time, but often in DP on tree problems, we can do this. And then, yeah, we can either do like top down or bottom up. And our state is often the subtree. So we have some sort of tree. Our state is often given some subtree like this, and maybe some extra information to solve the problem. We represent a subtree by the root of the subtree. So generally in tree DP problems, if we say DP of a node, and if I say DP of a node, I mean DP of the subtree that node is a root of. The DP of this node over here is DP of this subtree. But yeah, it's much easier both in code and like conceptually to think of subtrees by their root node, so we do that. We might store some extra metadata. Depending on the problem, this will become clearer when we solve problems. And usually we do these top down. Not always, but generally we'll do tree DPs top down. Just because that's what is easier to do when coding up tree DPs. Unlike DPs on like arrays, where doing a for loop over an array, super easy. Doing a for loop over a tree, it's not as easy as doing it over an array. So generally top down just works nicer. But again, generally doesn't mean always, but quite often. Okay, so the first problem is weighted maximum independent set of a tree. I'll explain what that means. We're given the description of a tree, so like the edges, and also each vertex has a weight. And the question is, what is the maximum sum of vertex weights of some set, which is independent? A set is independent if no 2 nodes share an edge. I'll give an example of this in a second. It'll hopefully make it a bit clearer. Here is the example. This is a tree, but independent sets. So, for example, 3 and 5 is an independent set of weight 8, because weight 3 plus weight 5. 1, 2, and 1, 4, and 2. Let me delete these old ones. This is also an independent set of weight 5, 7. With no to-node adjacent. This here is not an independent set because we have adjacent nodes in our set. The same argument, ignore this line. This here is also not an independent set. These two are adjacent. In this problem, this here is a maximum independent set. Weights is 9. This is the best you can do in this case. 3 plus 4 plus 2. So the answer to this problem, given these nodes and these edge weights, is 9. So if there's any questions about what the problem's asking, let me know. Otherwise, think about how to solve this using DP on a tree. So it seems like, I guess, set up to justify why we're using DP, it kind of seems like we either include the root, in which case we do some stuff, we don't include the root, otherwise we do some stuff. In that case, you can kind of think about it like a recurrence. It's just kind of like a vague justification as to why we might use DP, as to why you might think about using DP, just because it kind of seems like you have a subtree or a node, you can either include it or don't include it, and based on whether we include it or don't include it, changes stuff, because if we include ourselves, we can't include our children, etc. This is kind of like, yeah, just a hand-wavy justification as to why I might do this. If we order trees down from the root, or arbitrarily root trees, and think about subtrees like we would on a rooted tree. Even though the tree we're given is not rooted, we're going to root it arbitrarily because it will make our life easier. So I guess a first step of a state is just, given a subtree that is a vertex, what is a maximum weighted independent set in this subtree? If we can solve this, obviously the answer to the question is just the root of the entire tree. What is the maximum independent set in that? And then if we can solve this for each subtree, then we can get the answer. Let's consider recurrence. We have two options. We either include U in our MIS, our maximum independent set, or we don't. Let's consider the case where we didn't include U. Then if we don't include a node, let's say we have 3 children, then we're free to include our children if we want, or we're free to not include our children. Like, we don't have to, but we're free to if we want, which means the answer is just what is the maximum independent set of this one, of this one, of this one, and we add them together. The reason is because, yeah, we have no constraints over the sets because we haven't chosen this node, so we're free to do whatever we like. And because it's a tree and not a DAG, children are independent of each other, and so we can just get the max independent set of these 3 and add them together. So we can just go, yeah, sum of my children's DP value, that is my DP value if we don't take the root. If we do take the root, however, then we want the best MIS, but that MIS can't include the children, because we take us by definition of independent set, we can't take our children. So we want the best set of our children's subtree that doesn't include the child. But in our state, we don't have access to this information immediately because we just have what's the maximum independent set of a node. Maybe, since it's useful to know what's the max independent set without the root, maybe we could amend our state to give us 2 options. One option is max independent set, just like of that subtree on its own, or max independent set that does not contain the parent. Like, given a tree, let's say we had weights, this is our subtree, with weights 2, 3, 4, we've got a subtree of size 3, and the answer to what's the best independent set of the entire tree, well, it's 10. However, best independent set that doesn't include the parent, or the root, sorry, that's these 2, 7. We're going to have two times n states. State 1 for a subtree, and remember subtrees are represented by their root. Case 1 is we can include it if we want. We don't have to include it, but we can. Option 2 is it doesn't include it. Explicitly does not contain u. That's this one here. And then how can we compute these? Just formal definitions. So f of u, we'll say, is the maximum weight of the independent set that contains u, and g of u does not contain u. So we're gonna, rather than doing can we maybe contain or can we not contain, we'll just, for simplicity, we'll do explicitly f of u means we contain u, and g of u means we do not contain u. Put these together, like what is the best one overall? Just a maximum, because two options either include or don't include, and so the best with no constraint over including or not including is just take the maximum of them both, of f and g. Okay, recurrent. Let's consider an independent set that contains the root. Then we must not take the children. However, if we don't have the root, then it doesn't matter whether to take children or not. Because if we don't take our root, then we have freedom of taking our children. So I'm going to call the set of children n of u, just the notation we'll use. Then we have f of u. This is if we include, I'm not going to write too much, but this is if we, that says include. This is if we include u. Writing is hard. And the options are our weight, that's the weight of u, plus for each child, g, which is do not include. So we're taking us and the maximum of all our children if we don't include those children. If we don't include ourselves, then for each child, it's a maximum of, well, include that child or don't include it. Because if we don't include some node u, we're not necessarily obliged to take the children. We can take them, we cannot take them. So for each child, we do the maximum of take and not take and add them up. And that's essentially the DP described. If you have any questions, let me know. Otherwise, we'll keep analyzing it. Base cases are just, if we're a leaf, then the maximum set which contains us is, well, just us. The maximum set that doesn't contain us, that is G, is nothing. A fairly simple base case. Okay, so the complexity. We have order n states, one for each node. And it seems it takes order n to calculate because we can iterate over up to order n children. So naively, we might think, well, it's n squared. But importantly, each vertex v only appears as like right hand side. That means in the recurrence. So only in a recurrence, i.e., it only appears, each node is only the child of one other node, which means that the sum of recurrences across all nodes is n, or in other words, the sum of the numbers of children of all nodes is n. So the sum of all recurrences is order n. Even if like one node has lots of children, that means other nodes have less children. So over all nodes, the recurrence is order n, which means overall DP is order n, not n squared. Order n, that's fast enough to pass for this problem. In fact, it's the fastest you can do because the tree is of size n. So we have an order n solution. This is the code. So we're calculating the weighted maximum independent set at some node u. We say, okay, I guess the initial values, the base cases, are f of u, just take ourselves, g of u, take nothing. And for each child, we calculate that child's value. So we're going top down. We calculate that child's value. And then we say, okay, f of u, that is, we take us. Therefore, we don't take our children. G of u, we either take or don't take our children. This is identical to the previous slide. So nothing crazy going on here. It's just the code version of the previous slide. That is this problem done. Any questions, let me know. This is kind of an example of a fairly basic tree DP problem. You might, a sort of problem, you might see a problem like this, like it's not impossible. So yeah, example of a tree DP problem. The second example we're going to go on to now, a slightly more involved 3DP problem. This is kind of an easy one. And we have kind of a harder 3DP problem next. In this problem, you're given a tree. So all the edges on that tree. You're also given an integer k. The question is just how many subtrees have size at most k? You have to calculate this modulo 10 to the 9 plus 7. What that means is if there's like 1,000 such subtrees, you output 1,000. But if there's 1,000,010, that is 10 to the 9 plus 10, you output 3. The reason is just because the answer can be very large, like, well exceeding a long. And so this is just here so that you don't have to output like a 1,000-digit long number. It doesn't impact the problem otherwise. So you can kind of pretend it's not there. Code it up. Here's an example. So if k equals 3, we get this tree here. Then how many subtrees are there of size 1? Well, we have 5. It's just like this node on its own, this node on its own. They're all subtrees of size 1. Note, when I say subtree, I don't mean rooted subtree. So like before we describe subtrees, we meant like subtree of 2 is this. When we say subtree here, we just mean set of nodes in the tree that are connected. There are 5 subtrees of size 1. There are 4 of size 2. That is this, and the last 2, this and this. And then there are 4 of size 3 as well. They are this here. And then there's like this, and this. Bit messy, but like I can't think at the point. There are 4 of very messy diagram, but yeah, there are 4 of 5 of size 1, 4 of 2, 4 of size 3, which means k equals 3. How many subtrees have size at most k? 13. We're ignoring subtrees of size 0. I guess hard to define how many there are. We're ignoring them. So we say there are 13 total in this case. Any questions or confusion about what the problem's asking? If it makes sense, I'll go on to describing how we solve it. But obviously, if you don't understand the problem, you won't understand the solution. Okay. So yeah, a quick note, which I said before, the modulo 10 to the 9 plus 7 is there because the number of possible trees, I mean subtrees here, subtrees, could be very large, well exceeding a long. You can kind of think about it, you can get like to the power of very large, to the power of 1,000 or more probably. So we compute the answer as we otherwise would. Along the way, just modulo by this. Y plus 7. Yeah, so this number is 1,000,000,007. So like, yeah, the reason is just because this number is a convention in competitive programming. You often see problems that are like modulo, 1,000,007,007. So like, I think it's this number. Put the zeros right. It's kind of just convention. I guess one reason, which isn't important in this case, because it's the first prime after 1,000,000,000. It being prime is not important to this problem, but in some problems, it being prime is useful. 1,000,009 is also prime. It's not important. But yeah, it is prime, which helps in some problems. In this problem, this number could be anything. The reason why they always give you a prime is because it means that in problems where like the primality is important, like if you just like only gave a prime in problems where it was useful, they'll give it away. If you like always give a prime number, then like it's not obvious whether it's useful. So like normally we're given a prime number, and normally it doesn't matter. Yeah, which is a convention, so I'll put it here. Exactly, as Raveen said, for dividing, it matters, but for adding and subtracting and multiplying, it doesn't matter. So you can kind of ignore this in this problem. But if we needed to divide, then like number theory stuff, it becomes important. This is a counting problem. And so the DP will associate a state with how many subtrees can be created from this state. So we're going to have some subtree, we'll have some state, and then the answer is just how many subtrees can we create from this state. And we'll discuss states in a bit. But yeah, as Raveen said, division in modulo numbers is a bit of maths going on. It being prime means there's a unique solution. Otherwise, there isn't. But again, not needed for this problem. I just put it in there because it's a convention. So if you see 1 billion plus 7 in a problem, which you might, it's probably not super important. Okay. So yeah, our state can include the node, which would be a root of our subtree. As we discussed, that's typical. So we're gonna root the tree arbitrarily because why not? And our state will involve some node, which implies its subtree. But also we're going to store some additional information, because if we just store the node, we don't have all the information. Because if we're at a node and we want a subtree of size 3, that's obviously going to be a different answer than if we're at a node and we want a subtree of size 4. And so it makes sense that then our state might include the node we're at and also the subtree size we want to create. So for example, we're here. Let's say I have 2 children. It's our bigger tree here. But if we're at this node here, the circled one, and we're going to create a subtree of size 1, the answer would be 3. Okay, a subtree of size, in our state will say a subtree of size exactly k, or exactly size 2, 2 options. Size exactly 3, there's 1 option. So our state, yeah, is some node. Considering only nodes in that subtree, what's the biggest subtree you can make? Yeah, I'm using 2 definitions of subtree. When I refer to a state, I mean like the rooted subtree. In the actual problem, I'm referring to like any subtree. So yeah, our state will be root of the subtree and number of nodes we want to have in this subtree. And we're going to have exact rather than up to in this case. But if we can compute this DP, then what's the answer to our problem? Well, it's just the sum across all nodes, the DP value for all subtree sizes. That is because every subtree in the tree, like from here, for example, every subtree, we've got a tree, has like some root. And so if we just add up the DP values across all nodes, we'll get all subtrees. So we get our answer. So like if we can compute this, that's still an if, just like our first suggestion. But if we can solve this, then we can solve the overall problem. Cool. Now, what we'll consider, like, what could our recurrence be for our state of node and size? Well, we're gonna if we're gonna create a subtree of size k, for some k, could be different to the k in the like just any k. We're gonna first of all include this node because we have to. That's the definition of like the state of subtree with this node as a root. And also, we're going to distribute the k-tech1 non-root nodes between its children. That I mean, like, let's say we have 2 children. Make a subtree of size 5. We have 1 here. We have 4 left over. We could have all 4 of those nodes here. So like 1, 2, 3, 4. We could include 2 nodes from this subtree and 2 from this subtree, etc. So to count the number of subtrees, we want to take one for ourselves and distribute the rest over our children. And one idea would just be to try every way to distribute our children. So like, for example, give 5 to our first child, 3 to the second child, etc. I'm just like to try that. The issue is there are a lot of ways to do this. If we have one child, there's only one way, right? We take one node for ourselves and give the rest of the k plus take one to our children. So our occurrence would be like, well, occurrence would be like dp child k minus 1. If we have two children, there are k ways to do it. We can give 0 to our first child and k take 1 to our second child. We can give 1 to our first child and k take our second child, etc. All the way up to we can give k take 1 to our first child and 0 to our second child. We could add up all the states for those two and get our answer. But the problem is, if we have C children, there are this many ways to distribute the k take 1 nodes among them. This exact number isn't super important. All that's important is like, this is big. If we have 10 children, the number of ways to distribute 100 nodes among 10 children is massive. We don't have time to compute all of them. So we need a better way to calculate our occurrence, because the naive idea of just try every way is too slow. But let's quickly just analyze the complexity of this idea on a binary tree. So to recall, the idea is our state is the node we're at and the size of our subtree. Our occurrence is consider all the ways to distribute k take 1 nodes among our two children. There are k of these. Add them all together. Now there are order nk states, n nodes, k sizes, and the occurrence is order k, which means you have an order n times k squared dp on binary trees. This is fast enough to pass, because 1,000 times 100 squared, 10 million. But the issue with this dp is it only works on binary trees. As soon as we have 3 children on a node, it becomes too slow, because our recurrence becomes approximately k squared on 2 children, approximately like k to the number of children minus 1. That's from the like entries k from before. But the important part is this works on a binary tree, but not on other trees. The reason why the solution is efficient is because we have k options of how many nodes to give to our first child, and then we just give the rest to our second child. For an arbitrary tree, let's try something different, something similar, sorry. And kind of this is the key point in this problem. We're going to pick some number of nodes, give to our first child, and rather than like distributing the rest among the remaining children, we're just going to say, give like 5 nodes to our first child, that is dp of first child 5, and then just give the rest to the rest of our children. And how we handle that, well, that'll become clearer on the next slide. We modify our state. Our new state is root of our subtree and number of nodes, same as before, but also child that we're up to. What I mean by that is we have a node with 3 children. Let's fix the size. Let's say size 5. We have 3 states. We have dp5 first child. In that case, we try giving some number of nodes to this, and then from there we recurse into dp of this node 5 second child, this node 5 third child. Why that's useful is because we can do the idea of give some to our first child and give the rest to the remaining children. Because as an example, I guess I won't go over details yet because they'll come like in one slide, or like later on this slide. But we're saying dp ukc means we're at the subtree u. The subtree will have k nodes in it, including u, that is including the root, and also the subtree will not include the first c children of u. This is the same thing as child we're up to, because like if we're up to the second child, if we zero index up to child 0, up to child 1, up to child 2, if we're up to child 2, this just means we're not considering the first 2 children because we've already considered them. And what this means is we'll go over the recurrence. Let V be the cth child of U. That means let V be the child we're up to. C means the child that we're up to. And the recurrence for this DP is if V is the final child, then this is quite similar to the one child case because we must give all remaining nodes to our child, except the one we keep for ourselves, the root. So in other words, the answer to DP UKC, if C is the final child, if V, which is the cth child, is the final child, is just DP of the child. We're giving it K-Tech1 nodes. And also, we started the first child of that node because we kind of start again at that node. So this here is just, if this third value is 0, that means we don't ignore any children. So that means that that's just ways that to distribute K-Tech1 nodes among this subtree. However, if V is not the final child, then we're going to try giving some number of I nodes to V less than K, because we need to save one for ourselves, and give the rest to just the remaining children. That I mean the sum of, for all I, this here, this first value, dpvi0, number of ways of giving I nodes, of building a number of ways to build a subtree of I nodes rooted at V as a child. So we have like U here, V. So like, for example, if we want to make a subtree of size 5, we can give 2 nodes to this one, and we give 3 nodes just to like the rest. This here, dp of U, same node. K-Tech I, because we've given I to this, so we only have K-Tech I left over. And C plus 1, because rest of the children. In other words, pass it along to the next child. We multiply here because we're counting. And these two things are independent because number of ways to make a subtree of size I here, and the number of ways to make a subtree of size K-Tech I here are independent. So number of ways to do like the combined thing is we multiply them together because of the counting problem. And the base cases are K equals 0, that is make a subtree of size 0, or have no children. In that case, either K is 1, in which case, yes, we can do it. If K is 2 or more, we can't do it. Because if we have no children, we obviously can't make a subtree of size bigger than 1. We only have 1 node. These are our base cases. This recurrence makes sense. This is, I guess, probably a new and confusing idea, but also kind of important. So often in tree DP problems, in harder tree DP problems at least, you often need to have this child idea. So rather than having DP of just a node, you have DP of a node and a child. This allows you to efficiently distribute things among all your children without doing it all at once. That's kind of the idea. We're going to distribute K nodes or K-Tech1 nodes among our children. We do it one child at a time. We have different states for it because this makes the problem a lot easier. Because otherwise we're redoing work, and this saves us from like doing work over and over again. If there's no questions, I'll go to the code, which is, first of all, analyze complexity, then go to code. The code will just be this in C++, pretty much. So how many states are there? Well, naively, we have n times k comes from n nodes, size up there. The n squared comes from the fact that we have 1 state for each child. There could be n states per node, so n squared k. However, same as the last problem, the sum of children across all nodes is order n. Because each node is a child of one other node. So the sum of the number of children across all nodes, is order n, which means they're actually order nk states. In other words, this child state idea does not increase the number of states from a complexity point of view, which is nice. The number of states remains the same. The recurrence at each state is order k, because if you go back, doing k things here. Means we've got n squared dp, because nk states, k recurrence at each state, order nk squared. This is, for the problem, 1,000 times 100 times 100, 10 million. We have a solution that passes for the bounds in the problem. So in terms of coding it up, so often these kind of DPs, these kind of tree DPs, where you distribute nodes among children, can be quite daunting to code up. Like I remember when I coded this up, like even when I was coding this up, it's quite daunting because it's kind of a convoluted state. I think this implementation is actually fairly nice. So this is just edge adjacency list. This is just the edge list for each node. It just stores the edges in the children. For simplicity, we're assuming we already filtered this list. And so we only have edges down the tree. In other words, we're assuming our tree is already rooted. It's pretty easy to root a tree, just like do a DFS and just add the directed edges. So we're assuming the tree is already rooted because it saves us time. This is f, we'll store our DP value. We have a vector. That's because our state has three things. That is node we're up to, k, like size of subtree, and also child number. We have vector because like it's different size for each node. Again, we assume when we call this DP, each vector has a length equal to the number of children it has. And initially, we'll assume this vector is initialized to net1. On the next slide, we'll actually do that. But, okay, that's just kind of setup. Our DP says, best case number 1, we have no children. Then the answer is true if we've got a subtree of size 0. We say there's one way to do a subtree of size 0 because that base case is what works, because let's say like at some root, we want to give 0 nodes here and all k nodes here. Is to return 1 because we want 1 times this. So number of ways to give 0 nodes we say is 1. The number of ways to give 1 node is also 1. But if we have no children, then obviously if we want to make a subtree of size 2, that's impossible because there's only 1 node. So return 1 if k is less than or equal to 1 or 0 otherwise. That's base case number 1. Base case, this here is just like our memorization. So like if it's before, then return it. This is best case 2. K is 0. We return 1. Same reason as I just described. And this is kind of our setup. Below this line is our actual DP. So this is the same as 2 slides ago. This says if we're the last child, if child plus 1 is the number of children, to 0 indexed, we just return, well, this is what I described 2 slides ago. That is, give all our children to the child. Case 2, not the last child. Again, same as before, we iterate over all k from 0 to k take 1. All I, sorry, from 0 to k take 1. And we go, okay. Okay, so this is number of ways. So this first one, yeah. Number of ways to give I nodes to child. That is number of ways to make a subtree of size I. To make a subtree of size I in my child, like in a child. And this is, that's the first thing here. That's this. this here is number of ways to make a subtree of size k take I for the remaining children. That is, this is identical to 2 slides ago. Let's return the answer. Okay. Any questions about this? And this is just kind of our setup. So scan the input. We're assuming the edges are directed down the tree. Again, if they're not, just do DFS to make it that way. Then here we just make all our vectors size and initialize them -1, as we guaranteed here that we would. Just call the DP for every value. And then we add, remember the answer was the sum of DP values for every node and every size, because the question is how many ways to make a subtree of size k. So we add for every node, for every size, add the number of ways. Regarding moduloing, I define mod up here to be equal to 1,000,000,007. And along the way, I say after every addition, we do a modulo. The reason is because this problem will overflow very quickly, because number of ways here, this number could be up to 1,000,000,007. Look at this number here, because they're both up to 1,000,000,006, because they're both moduloid values. So here we have a number 10 to the power of 18, which just fits in a long. But we modulo here. If we didn't modulo to the end, we kind of just like kept going, kept computing it, and modulo just once at the end, it could overflow. So modulo along the way, and same here, modulo along the way, and put in the answer. Also, I use longs again because one other benefit of 1,000,007 that I guess what we missed before, the reason why first prime number above 1,000,000,000 is nice is because you can safely add 2 of these in an int, because add 2 of them together, get to 1,000,000,000, which means a problem that only requires adding modulo 10 to the 9 plus 7, you can do in an int. And any problem that requires multiplying, you can do in a long. So longs is sufficient for multiplication, as long as you modulo on the way. That's another nice thing about this number here. But yes, do it in long, we have our answer. Any questions? Otherwise, we've finished tree DP. I'm gonna have a quick break until 7:30. Feel free to ask any questions. Otherwise, we'll resume in about 6 minutes at 7:30. So yeah, as Raveen said, you can ask questions to him or to me. Just put them in the chat. Yeah, after the break, we'll go over some assorted problems using different techniques. Feel free to get a head start and read the problems if you want. No need to. I'll let Raveen answer that. So for the second question, how many operations can a computer do in 1 second? It's 10 to the 7 to 10 to the 8. So it's 10 million to 100 million, which is 10 to the power of 7. 10 to the 8 normally. Yeah, you're going to be stretched to do 1 billion operations in a second. Yeah, which is why, for example, for the B of contest 2, 5 million squared, 25 million is good. That's kind of in that gray zone again. But like how I think about it is, yeah, that problem B was kind of a fairly fast DP. Like there's not much going on, so that's fine. But like kind of a slow 25 million might time out, but a fast 25 million is fine, if that makes sense. Okay, half past, so we'll get back into it. And yeah, Raveen just answered the question about distribution of scores. So yeah, the rest of it, we have 3 sort of problems to get through. And then we have 1.5 hours left now, so not sure how much of this stuff we'll get through, but we'll definitely get through all of these. Okay, so this problem, ATM, we're given a city with n intersections joined by m one-way roads. That is, you're given a directed graph. At each intersection is an ATM with some amount of dollars. And also, some intersections, as well as an ATM, also have a pub. A bandit wishes to start at some intersection S, you're given S, wants to drive around, so walk along these directed edges, and at each ATM they get to, he steals all the cash from the ATM. And after doing this walk, wants to finish at a pub. So like there's a pub here, one possible walk could be like start here, rob all the ATMs, rob this ATM, then finish at the pub. You can visit a node more than once, so you can visit an ATM more than once. However, you can only rob it once. Once you've robbed it, money's gone. So like you could, for example, if there's a cycle here, you could kind of go follow this path and then back and finish at this pub. That's perfectly fine, but you only get the money once. And the question is, what's the maximum amount of money that you can steal? So input, you're given the number of nodes, number of edges, number of cities, number of roads, intersections and roads. You're given up to 500,000. You're given m lines, each with the edge. So you know there's a directed edge from U to V. Then given n lines, each one is a non-negative integer ci up to 4,000, representing the cash that is at an ATM. Then given S, that is the starting intersection, and P, the number of pubs, and you're just given where all the pubs are. And the output is just a number. What's the most money you can steal by starting at the start, traveling along edges, and finishing at a pub? You are guaranteed, it's not written here, but yeah, you're guaranteed that you can finish at a pub. Yeah, so it's guaranteed there exists some path that is valid. Source APIO. So here's an example. So in this case, you start at intersection. You start at intersection 10. This is S. And these are the edges. Hubs are the double-lined ones. So for example, one valid path would be finish here, or you could go, for example, finish here, or like this. In this case, the optimal path is 1, 2, or a optimal path is 1, 2, 4, 1, 2, 3, 5. Note we get $10, $12, $16. We don't collect this again. We only collect it once, so we get nothing again, nothing again. Then 8 and another 1. So answer is like 10 plus 12 plus 16 plus 8 plus 1, which is 47. And that is the maximum possible in this case. Now, if this wasn't a pub, if this was a normal node, not a pub, then a maximum answer would be 46, because we could just finish here. But because this is the pub, we can finish there, and our maximum answer is 47. Any questions about the problem? Otherwise, we'll go on to discussing it. So yeah, as I said, intersection on roads correspond to vertices and edges in a directed graph, because roads are one way, intersections are nodes. Fairly common like flavor text for a graph problem. I guess one observation is when you reach an ATM, you might as well steal all the money. There's no reason to not steal from an ATM, because every ATM has not a negative amount of money. So you're always making money when you rob from them. So you might as well, whenever you visit a node, just take the money. The graph can have cycles. Like the sample had this cycle here. And in that case, if we enter a cycle an important observation is that we might as well steal all the money from all the ATMs in a cycle. Because if we enter a cycle, we can start here, we can collect all the money, and then finish back here, which means any path that we could reach from here, we can reach after grabbing all the money. So, in other words, taking all the money from the cycle doesn't disadvantage us because we can end up back at the start after taking everything. So we might as well just go around, steal from the entire cycle. Yeah. We can always do a second pass. This approach, steal from every vertex and traverse it again, limited to cycles. Well, hopefully, like you can see, we want to take, if we're at some node, we can take everything in the maximal subset in which every pair of vertices can reach each other. Or like in other words, any vertex which we can we're at some node, any vertex where we can kind of walk to that vertex and then walk back to our node here, we might as well take, because we can go to that vertex, take the money, and come back here. And because we finished where we started, we didn't shut off any paths that we otherwise could take. So that's optimal to do. And same here, we can go a second path and get this one. And hopefully you can see this corresponds to strongly connected components. Because the definition of a strongly connected component is a subset where every pair of vertices can reach each other in a directed graph. And so we've just shown that if you're in some SCC, some strongly connected component, you might as well take all the money from that SCC, because we can take all the money without disadvantaging ourselves. So just do it. And also, because from in an SCC, you can travel anywhere else in that SCC freely because of this condition here. It doesn't really matter where we are in that SCC, just that we're in it. Because if we're at one node, because the problem doesn't matter how long it takes us to walk. So as long as we know what SCC we're in, that's all that matters. Which leads to the idea where we can treat each SCC as a unit. Because we only care which SCC we're at, not which node we're at in it. Because if an SCC has a pub, that means we can finish there. And we might as well take all the money in it. And any edge out of an SCC, no matter where it comes from, we can always reach it. So yeah, we'll condense the graph down into a graph of SCCs. Graph. Each vertex represents an SCC of the original graph. Every vertex weight is the sum of the vertex weights in the SCC. This corresponds to the idea that you might as well take all the money from all the ATMs in that SCC. So we're just in the big supernode for the SCC. We just add all the money together. And each edge corresponds to the original edge in the graph. So if there's an edge between node 1 and node 2, then if these nodes this is the original graph, then if these nodes are in different SCCs, we'll have an edge between their two SCCs in the condensed graph. So this is somewhat, I say common in quotation marks because it's not that common, but in SCC problems, sometimes we want to condense a graph. Normally this is how it's done. We have a node for each SCC and edges out of it. It's not super common, but when it does appear, this is often what you do. Now, importantly, this graph has no cycles. Why is that? Let's imagine that this new graph had a cycle. If it has a cycle, that means we can travel from every node, we can travel from every node here to every node here and then back again. Because we can travel from here to here and then back again. That means that all these nodes are in one big SCC, which is a contradiction because we'd already compressed our graph into SCCs, which means a graph of strongly connected components is a DAG. And hopefully, like if you remember SCCs from the last lecture, that is kind of the idea. We have a graph of DAGs. And so here's an example. This is like the example from before. So this is, if I go way back, example here, but we've compressed these, or if we compress these into one node with weight 10 plus 12 plus 16, 38. And these two are not, like, there are no other SCCs. This is the only SCC. And that, yes, 38 here. And then the rest of it as usual. So this is our compressed graph. Now I have a DAG. And now the answer in this DAG is just the longest walk that starts here and finishes at a pub. So go here, 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 or like here, here, here. And it's easy to see that, in this case, it's easy to see that 38 plus 8 plus 1 equals 47 is the best possible walk. And this problem is easier because there are no cycles. We can never visit a node again. And we'll see that this makes a DP a lot easier. So we're going to find the maximum weighted path in a DAG, starting at a given vertex and ending at some other vertex. And DP. So this, I have code for this, but the state is just the node you're up to. And the recursion is just like step 1, take all the money from here. Step 2, if we're a pub, or if we have a pub in our node, consider just ending our route here. So answer just like we've got is VI. Otherwise, all outgoing nodes take the maximum. And this will make more sense. I'll code on the next slide, or maybe a slide afterwards. Complexity. Finding SCCs with Tarjans or Kotarajus is n plus m. Again, if you're not familiar with this, I recommend going over last lecture because it was covered then. Build the condensed graph, n plus m. You're just iterating over all nodes and like getting the sum of all edge weights across in SCC, etc. Again, I'll describe this when we have the code. Topological sort, order n plus n for our DP. So our DP order n plus m. So topological sort is for our DP. In the code that I have, this is done implicitly with a top-down DP. Explicitly with a bottom-up DP would be a bit different, but yeah, it's kind of in one step, but still, overall, every step is n plus m, which means overall we have n plus m. Important part. Okay, here's the code. So step 1, yep, and longest path in DAG. I think talked about a lot. I think it was covered in last lecture, and also like I mentioned that talked about trees ages ago. So like yeah, this is Kotarajus from the last lecture. This is here. Everything up here is pretty much copy and paste. I changed one line to make it a bit easier, but like this is from here onwards, just copy paste. This is just like some setup. Again, this rewatch the last lecture or part of it if you want to understand what this is, but this is Kotarajus. This is just some setup. These arrays will be the value of an SCC and also whether that SCC has a pub or not. And these are our arrays for our DP. They're on this slide because size, they don't fit on the next slide, essentially. So here we have our DP. So if we start at SCCA, what is the most money we can take? The simple DP, just the answer is negative infinity. unless we have a pub, then we can end here. This is like end here. Otherwise, for each outgoing edge, we take the biggest of our current answer, and also if we want edge, which is dp of that edge plus our value. And return that. Again, longest path on DAG, fairly standard dp. In our main function, we take in the input. In CoSarajus, we need a reverse edge adjacency list as well as a forward one. That's why I've got that here. So here we compute the SEC graph. So we call our compute SEC function. That's this here. Importantly, this creates an array called SCC, where SCCI is the index of the strongly connected component that I is in. We use that here. We say we add edges. We say for each node. So for each node here, for each node, we iterate over all its edges, and we say if the SEC of like me and this edge are not the same. In other words, if this isn't like a self loop in the SEC graph, then add this edge. So go SEC edges like this, dot push back this. This is just adding it to the adjacency list. Like we're saying my SCC has an edge to your SCC. So in this case, we might have duplicate edges because if we have like two SCCs with like two nodes here, like here with two nodes. If we have, for example, this edge and this edge, then we're going to include that edge twice. This isn't important because the DP, like that doesn't break the DP. In cases where it might break the DP, you gotta be careful, but in this problem, that's not important. So like, I guess a note is sometimes removing duplicates is important. In this problem, it is not. Oh, what have I done? Lost. Oh, I'm back. That's fine. And then here we just scan the values. This is the the amount of money, and we just say, okay, add that to our SEC's total, and then we mark SECs as having pubs, and then we just do the DP. The code's pretty simple, which is nice. If there's any questions, let me know. Otherwise, I'm going to move on to the next problem. And that is night out. So in this problem, you have a street with n restaurants, each with some distinct rating. For each of Q nights, you want to visit the highest rated restaurant in a range. However, you don't want to visit the same restaurant like twice. In particular, if you visited a restaurant in the last K nights, you ignore it. Input NK and Q all up to 100,000. You're then given n distinct integers. That is the value of your rating of that restaurant up to 100,000. You're then given Q lines. This is the start and end of the range for a given night. I'll put two separate lines. What is the restaurant you visited on night I? If there's no valid restaurants, print -1 from all right. So an example here, we have 5 restaurants. K is 1, which just means we can't visit the same restaurant twice in a row. And then 4 queries. Query 1, we're going to go to some restaurant from 2 to 4. Let's get the output here. We'll go to some restaurant from 2 to 4. We go to the biggest one, so we go to this one here. That is restaurant 3. Night 2, we go to the highest rated restaurant from 2 to 3. However, we don't visit the same restaurant 2 nights in a row, which means we don't go to this one here. We ignore this. Instead, we go to the next highest rated restaurant, this one here, restaurant 2. The third night, we go to some restaurant from 1 to 2. But we can't visit the same restaurant twice in a row because K is 1. So we can't visit here. So we must visit here. Note that if this query was 1, 3 instead, we would be allowed to revisit this node here because it's been 2 nights and K is 1. But obviously in this input, we have this one here, so we can't visit here, we visit here instead. Final input, we're given 1, 1. Now, since we visited this node on the previous night, we can't visit it. We can't visit any restaurant, which means -1. We can't visit anywhere. That's the example. Any questions about that? So it's just highest rated restaurant in the range, ignoring any restaurant we visited in the last K nights. Okay. So I guess one important thing is, as it says, we need to find the maximum in a range quite quickly because we have a bunch of queries of the form like, given some range, what's the maximum, excluding the previous K nights, which involves finding the maximum in each range. And we can't iterate over everything. That would be like 100,000 squared, which is 10 to the power of 10, which is too slow. So we can't do that fast. So we need at least a fast way to find, given some range, what's the maximum value. So one way is a sparse table, covered in lecture 2, I believe. This is n log n pre-processing, constant time per query, but inflexible because we can't do updates. A sparse table is static. Once you build it, you can't change it. A segment tree, on the other hand, n log n pre-processing, or order n, n log n is fine, and log n per query, so given a range, what's the maximum, and also can update it, which we might find useful when solving this problem because of we can't take the maximum we took before. So if we can find the maximum value in the range, we can quickly find which restaurant it corresponds to. This is because each restaurant has a unique rating. So if we get the restaurant of rating 10, we can have a lookup table which has like for each rating, what restaurant has that rating, which means we can look up quickly what restaurant that is. If the rating is 100,000, so an array is fine. If the ratings were up to like 1 billion, for example, we couldn't have a 1 billion length array. That's, I believe, 4 gigabytes size-ish. Too much, probably. So instead we use a map. One other thing is that we can actually use segment trees. So normally segment trees return just the value, like the maximum value, for example, and not maximum value and node. In both sparse tables and segment trees, we can get it to return the index of the maximum value if we want. We do that by keeping track of the index. Another way of thinking about it is if we use a pair of value index. If you've seen pairs in C++, the way their comparator works is it first compares the first element and then the second element. If you have a segment tree over pairs where each value is a pair of value index, and your segment tree automatically fetches the index as well, can be useful. In this problem, we just use lookup arrays though instead. Okay. But yeah, the complication in this problem is the fact that when we visit a restaurant, we can't visit it again for the next K nights. However, we can use updates to account for this. So you have to use a segment tree because sparse tables, no updates. How does this work? Well, if we eat at a restaurant, we can change its rating to 0. This is because all ratings are positive. So if a restaurant has rating 0, we're not going to pick it unless it's the only choice. And then K nights later, we can update it back to its original value. So we eat at the restaurant, we set its value to 0. K days later, we set it back to its original rating, which means any queries in between will essentially be ignoring this value, which is what we want in this problem. That's the solution, essentially. It's n log n pre-processing to create the segment tree. In queue times, we perform 2 updates. Update 1, we first perform a query, that is, find the maximum value. We then go, okay, like remove this value from our range, like set its value to 0, and then also do the update from k nights ago. So 2 updates plus 1 query, log n each, so log n plus q log n overall, which is again fine. 100,000 times 17, or 200,000 here times 17-ish. 3-4 million. It's fine. So here's some code. So this here is a segment tree code from the first lecture. The only difference is that we've got maximum here. In the lecture, you're given a sum one, but the maximum is the same thing. Are people comfortable with segment trees? Like they would know, obviously, like they haven't appeared thus far in contests, I don't think, but like they could appear in contests and exams, so good to know. If you're not sure, yep, they're good to revise in the first lecture, but this is the code from there. This is our query code. Again, the only difference is using max instead of sum. Otherwise, this code is copy paste from lecture 2, sorry. So again, to review segment trees, go over lecture 2, or read one of many online resources. And this is the actual code for the problem. So what are we doing? So here, we scan the input. We have a reverse lookup array. This array was given a rating. What is the index? So here we say the rating value I corresponds to index I. This update function updates our segment tree. So we're saying index A, value V, and that here. So this just creates the segment tree initially. Then for each query, we go step 1, scan the input. Step 2, doing 2 steps in one. First, we're doing the query. The plus ones here is because this segment tree code takes an inclusive, exclusive range. That choice is kind of arbitrary, but it's what this code does. However, the problem statement has an inclusive range. We add 1 to make it inclusive and exclusive. We do our query. We then do a reverse lookup, which finds the index. Then we say, okay, update the index, set it to 0. We then say, we print the answer. If the index is non-zero, we print the index. However, if the index is 0, index 0 corresponds to no restaurant, and print -1. Problem said, if there's no restaurant, print -1, so we do that. We then just mark this one as removed, so that k days later, so if I is greater than k, we unremove the restaurant. So we update the restaurant we removed k days ago and set it back to its value. Does that make sense? So we just unremoving the restaurant. And this is exactly the solution described on the previous slide. Okay, that's a problem done. We have one last example problem today. This is a harder problem. So the other 2 problems, ATM and night out, I would say are fairly standard applications. If you know SCCs, and if you know segment trees, XDP as well, those 2 problems should be fairly easy. Not easy, like Not super easy problems, especially ATM, but they're not extremely difficult. I think they're reasonable that you'd solve them. Maybe not instantly, but you could if you knew the techniques. Breed, on the other hand, is this is more of a, it's still on syllabus, but it's more of a challenging problem, at least in my opinion. So the problem statement is you have a rectangular cake with R rows and C columns, so an R by C cake. R, C, that's the wrong way around. R by C. You want to make K cuts, cutting the cake into K plus 1 pieces, but you must obey the following rules when cutting. Each cut must be made parallel to the sides of the rectangle. So here's our cake here. In fact, let's just go not blue. Red. Here's our cake here. We can't cut like this. That's illegal. We can cut either horizontal or vertical. Step 2, each cut must begin either on the left or the bottom and continues until it hits the opposite side of the cake or an existing cut. What does this mean? Cut 1, we can start here, for example, and we keep going until we hit here. But now, if we cut from this side, we keep going till we hit here, and we stop cutting. And now we might cut here. We keep going there. If we cut here, then we keep going till we hit here. If we cut here, we keep going till we hit here. However, we cut this cut here, for example. That's not. Why? Because we must start all our cuts from the left or the bottom, because we can't cut here. Now, you're guaranteed when you cut like this, K cuts will make K plus 1 pieces. Why is that? Each cut splits one piece in half. So we make one piece each cut. So we have the one initial piece, so K plus 1 pieces, like 1, 2, 3, 4, 5, 6. 6 pieces, 5 cuts. Okay, finally, there are only H allowed locations for horizontal cuts and V vertical cuts. What that means is there's some locations, like maybe here, here, maybe here, 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 and here, and here, 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 and here. You're allowed to cut on those locations, but you're not allowed to cut anywhere else. So we could cut like this, that's on that line, but we can't cut here because it's not an allowed location. And the problem says you would take the largest slice. However, you don't want to appear greedy. So what you're going to do, you're going to cut the cake slices in such a way that the area of the biggest slice is minimized. So input format, you're given R and C, size of the cake, K, number of cuts, H and V, number of horizontal allowed cuts, number of vertical allowed cuts. You're then given the coordinates of the allowed horizontal cuts, that's these here. You're given them in ascending order. Then you are given the allowed locations of the vertical cuts. So like here, for example, and here, in ascending order. Bounds, grid size is up to each dimension's up to 2, like at least 2, and up to like 10 to the 9. So the area is up to 10 to the power of 9. Also, the number of H and V are up to 1,500 each. And the number of cuts you have to perform is at most the number of allowed cuts, because obviously you can't perform more cuts than you're allowed to make. This guarantee just makes the problem like insane. But the important bound is this one here. They're up to 1,500 of each of the 2 allowed cuts. The source is Fario. Here's an example. So sample input, 6 and 8. That means this dimension here, 6. This dimension here, 8. there are 2 cuts you're going to make. There are 2 allowed horizontal cuts, 3 and 5. There are 3 allowed vertical cuts at positions 2, 5, and 6. And so one possible method, if we ignore the cuts they make, we could, for example, let's say our first cut is here and our second cut is here. Then our slices would have area, this is 2 by 6, we have 12 here, 12. We have 4 by 6, 24 here. And we would have 2 by 6, 12 here. The maximum slice would have area 24. Alternatively, if we did the first cut here, second cut here, maximum slice would have area 30. However, if instead, if instead we cut that, instead we cut here, here. So first cut at position 5, second cut at position 3. Then our total area of this slice is 18. This slice is 15, so this is 6 by 3. Sorry, 6 by 3. This cut has area 15, 3 by 5. And this slice has area 3 by 5, 15. The maximum slice has area 18. And this is the minimum possible maximum. That's the answer, 18. Does this question make sense? Importantly, there are constraints on if we can make and so slices we can make. Yeah. I'm just gonna get a drink quickly. So I guess I'll be gone for like 1 minute. So there's a 1 minute break. Feel free to ask any questions. I'll be back shortly. Talking for ages is hard. Okay, so that's a problem. So now we'll discuss the solution. So first observation, given some sequence of cuts, there always exists a way to reorder the cuts so that the horizontal cuts occur in descending order as do the vertical cuts and the same slices are produced. What do I mean by that? Let's say we do some slices. First cut, so cut 1, I'm going to do here. And I'm going to assume that all my cuts are on allowed cut locations. For simplicity, I'm not going to draw them. Let's say cut 2 goes here. Cut 3 goes here. Cut 4 goes here. Cut 5 and cut 6. Now in this case, these cuts did not occur in descending order. We did this cut, then this cut, then this cut, and same here, this one, this one, this one. However, by reorder, I mean, we can instead say, okay, this was cut 1, this was cut 2, this was cut 3, this was cut 4, this was cut 5, and this was cut 6. In this case, the vertical cuts occurred in descending order, 1, then 2, then 6. The vertical cuts also occurred in descending order, 3, then 4, then 5, like this one, this one, this one. This observation makes sense. The hand wavy proof is that because we can always cut from the left, so I guess I've got the more formal proof here. Okay, the idea is that when we do this cut here, we essentially block everything on this side from future impact, because no horizontal slice is ever going to get past us again, because you can't get past us, which means any future slice here is not going to be impacted by any future slices here, which means we could kind of, instead of doing this slice and then later doing this slice, we could do this slice immediately before doing this slice, do the bigger one first, and produce the same output. And that's essentially the proof of this observation. This is a key observation. So like, if you don't understand it or you have any questions, let me know. Otherwise, I'm going to move on to discussing this. So this is just what I said. We can assume that they occur in descending order, because if there exists a method to do them in descending order, then we can safely assume that they happen in descending order. It also means that if we know, or this is a different observation here, if we know the smallest horizontal and vertical cuts, and by smallest I mean yeah, I mean like the first one up here and also the first one along here. If we know these cuts here, then we have enough information to identify the remaining uncut cake. This way around, it's actually this way around here, because we can only cut from, sorry, my bad. Since we can only cut from the bottom and the sides, and because we're assuming our cuts occur in this order and this order, if we know this cut here, that is the lowest vertical cut, horizontal cut, sorry, and this cut here, the leftmost vertical cut, and the remaining real estate we can cut in is just this here, which means we can kind of describe our state by our last horizontal cut, last vertical cut. It doesn't matter which cut we did up here, but they don't impact any future cuts, and that's the important observation. As I said, this essentially inspires a DP, where the state is the smallest horizontal and the smallest vertical cuts that we've performed so far. And each state will find the minimum area of the largest slice, only considering future cuts, which is essentially what our DP would find. However, this state is not enough information. Why? Because the number of cuts remaining impacts the answer. We don't just care about like this and this. We also care about, do we have no cuts left? Do we have one cut left? Do we have two cuts left? They all impact the answer as much as just knowing the states do. And because of that, we can modify our states slightly. So it stores the smallest horizontal cut so far, the smallest vertical cut so far, and the number of cuts remaining. However, DCP will work, and you can have a DP like this that works, or like works in quotation marks. It's the correct answer. However, there's too many states, because we already have H times V times K, which is already 1500 cubed states, which is already too many states to solve a DP. No matter how fast the recurrence is, even with an order 1 constant time recurrence, we have more than 1 billion states. So this DP is it's, TCP is kind of a lost cause, to be completely honest. So let's try something else. However, we're going to try and binary search the answer, because remember, this problem was maximize the minimum and minimize the maximum, sorry. We have to minimize the maximum slice. And minimize the maximum, just like maximize the minimum, inspires binary search. Like, it doesn't always mean binary search, but it often does. And maybe this problem, along with problem A of the contest 2, is kind of proof that maximize the minimum and minimize the maximum often do mean binary search the answer. Not always, but in this case it does. So let's solve a decision problem. Let B of M be true if we can perform k cuts with the largest slice having an area of at most m. This just means, is the answer at least m? Is the answer at most m, sorry. Is the answer at most m, is what this is saying. Now, notice that the maximum slice having an area at most m is the same as ensuring that all slices have an area at most m, because if the maximum slice has an area at most m, then all of them do. So our problem is, our new problem, that is our decision problem, is we're going to say, what is the smallest number of cuts required so that every slice produced has an area at most m? We slightly modify this problem from can we do it in k cuts to what is the smallest number of cuts required so that every slice has an area at most m. The reason is, if we can solve this problem, then we just check, is this answer at less than or equal to k? Because if we can do like k take 2 cuts such that the maximum slice has area at most m, then we can do like 2 extra cuts anywhere, and the condition is still true. So we just have to minimize the number of cuts, then check, is that less than or equal to k? If true, B of m is true. Otherwise, B of m is false. What motivated the change from can we do it in k to what is the smallest number? The motivation is that maybe we can DP this problem. And why do I think that? If you remember, we kind of had a DP before where the state was the smallest horizontal cut and the smallest vertical cut. And we had to talk about minimum slice. But in this case, we'll see that this state is enough for this problem here, which is why I considered it, because maybe we could DP it. This is kind of the inspiration. So yeah, our new problem, what is the smallest number of cuts required so that every slice produced has an area at most m? We try DP, kind of minimize cuts. Therefore, we do not need to store this in our state. What I mean by that is, before, if you remember, we had to store the number of cuts in our state. But because we're trying to minimize the cuts, that's the answer to our DP, which means that's not in the state. The state can just be the smallest horizontal cut and the smallest vertical cut. And our recurrence could just be try all possible next cuts which do not produce a slice of area greater than m. What do I mean by that? Well, if our current state is, so here is our cake. We've done some slices before, like, here, here, and here. In particular, our smallest vertical slice is this one here. Our smallest horizontal slice, this one here, I got them mixed up, sorry. Smallest vertical slice, this one here. Horizontal, this one here. So our state is kind of this rectangle here, or this slice and this slice. Let's say hypothetically, our allowed cuts are here, here, and here, 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 and here. Our DP recurrence could be, for example, try this cut here. Then, assuming this slice it produces has an area at most M, then it's a legal cut to do 1 plus DP of this. Why? Because the number of cuts required is 1 plus the number of cuts to partition this here. Or you could try this cut here. As long as this area is less than or equal to M, cut plus DP of this. Let's say this cut produces this slice is greater than M. Then we can't do this cut, so we ignore this state. Same thing here. Area less than M, we go 1 plus DP of this. Now what's the time complexity of this? Well, complexity of this is quite slow because we're considering we have an order HV state. What's H and V? H is the number of allowed horizontal cuts. V is vertical cuts, so that's like the number of possible like rectangles that can be remaining. And we're trying like up to H plus W other ones. So we have like a slow recurrence. This is too slow because this is already 1,000 squared-ish. Times 1,000 again is too slow. But important observation. If we have the choice between two horizontal cuts, we should take the one that produces the largest slice. Why is that? Well, we have this here, for example. Let's say we have the choice between this cut and this cut, and this cut. Well, the number of cuts to partition this is going to be no more than the number of cuts required for this bigger area. So greedily, we might as well make the biggest cut we can, as long as the area is less than or equal to M, and then try here. So our recurrence can just be take the biggest horizontal cut we can, and 1 plus DP of this. Take the biggest vertical cut we can, and try 1 plus DP of this. Take the smallest of those, and that is our answer. That's what we're saying. Our recurrence is to try two options. Option 1, our horizontal cut that produces the largest slice. And option 2, the vertical cut that does the same. How do we do this? Well, complexity, there are order H times V states. If we do the recurrence naively, it's order H plus V. By naively, I mean for each state, consider every horizontal slice. Keep going until we find the biggest one, which has an area less than or equal to M. But this one is too big now. And take that. Same thing for vertical cut slices. That's too slow. But we can recurrence order log using binary search. Why? So we have this slices. We can check, okay, this middle slice, does it produce a slice too big or too small? If it's too big, recurse on this side. If it's too small, recurse on this side. So in log n, we can find the best horizontal cut, and log n, we can find the best vertical cut. However, this is still too slow. Why? Because we're left with DP that's like H times V times like log of something, log of HV. But then, if you remember, we're already binary searching the answer. So then we have a second log on the outside for the binary search. And I'll like, overall complexity is H times V times log again equals 1500 times like, let's say 20 times 20 approximately. This is in the range of 400, 500 million. Too slow. Like nearly, but too slow. We want to improve the recurrence to constant time. How do we do that? 2 pointers. It's kind of vague. What I mean by that, the idea is, let's fix the horizontal cut. So we're saying this is our big cake here. We're saying consider all states that include this cut here. Then let's say the allowed vertical cuts are like this. And for each allowed vertical cut, we're considering this state here. And we want to find what is the furthest away vertical cut that produces an area at most m. What 2 pointers says is, let's start with the smallest one. So we're going to have 2 pointers. One pointer is the slice we're up to, and the second pointer is the earliest back we go. So we start here, and then we increase this pointer by 1. And we check, is this area less than or equal to m? Let's say it is. And that means this is the largest slice. We then increase this, and we say, is this area less than or equal to m? Yes. Okay. Then we increase this. And let's say this new area is now greater than m. Greater than m. We then go, okay, this slice is too big. We increase this by 1. We check again. Is this area less than or equal to m? Yes, it is. Okay, good. We then increase this by 1, let's say. Big. And then we, okay, this slice is too big. Increase this pointer by 1. Still too big. Increase this pointer by 1. Now this is good enough. Now this is the best cut. And increase this by 1. Maybe we'll leave this how it is because this area is still good enough. Then we increase this by 1. We have to increase this by 1, 2. It's called 2 pointers because we have these 2 pointers. And it's amortized order 1. Why? Because to calculate these order V things here, right? But to do that, we move our first pointer at most n times, or most v times, sorry. And we move our second pointer also v times. So while one pointer increase, like here to here, might cause a lot of individual increases, across all order v states, the second pointer gets increased order v times. So to calculate the maximum possible the best vertical cut for v states with a fixed horizontal width is order v. So order 1 each. We do this for every height here. We do the same thing for horizontal cuts, which means in order 1, we can find the best horizontal and vertical cut. At that point, it's just a DP. Let me know if that's confusing. I can explain it again. But that's the idea. This means we can solve the decision problem in order HV. This means we can solve the optimization problem. That is the original problem by using search in this time complexity, which is fast enough. Okay, here's the code. So this is our can be function using our binary search. This is the 2 pointers idea. So we say, okay, fix the horizontal cut. Then for each vertical cut, this variable cut is our pointer that lags behind, and j is our first pointer. So we increase j by 1. We then go, while this area here, that is horizontal cut I, that's horizontal cut, that's this height here. So we've got this height here times this minus this, that is this distance here, that is this area here. That's what this finds. If that's bigger than the allowed area, so area is the allowed area. If it's too big, increase this pointer by 1. keep going. This finds the best vertical cut for each state, ij, so like ij being this cut and this cut. Do the exact same thing here. Horizontal cuts, this is the same thing but flipped to the side. So our 2 pointers move up like this. Okay. Then, so we're still in this function here. We now do a dp. So the dp is just for each horizontal line, for each vertical line. We're finding, if you remember, we're finding the minimum slices required to cut each slice into at most area k. What do? We say, if we can just take this whole area, if this entire area is less than or equal to the required area, then no cuts are required, we're done. Otherwise, we take the horizontal cut. So we say, okay, take the horizontal cut, and it's dp of this state here, plus 1 for this cut. The same thing for vertical cut, so we say, okay, the best vertical cut, do dp of this state here, and then add 1. Our dp, as you can see, our dp is bottom up. So we choose arrays. We then return, is this dp less than k? In other words, is it possible to cut the cake into slices, each one with area at most area, using at most k cuts? If so, true. If not, false. We then just binary search over that. This is our binary search the answer. So we binary search. If we can do it, then we say end equals mid. That's because we find the smallest possible area. So like if this area is possible, recurse to smaller. Otherwise, recurse to bigger. Does this make sense? This is a more complicated problem. Certainly quite a hard one. But yeah, the idea is binary search the answer. Now, so far, like we DP in this one, so we've seen many binary search the answers where we do greedies. In this one, we do a DP. If there's no questions, that's the end of the on-syllabus content for today. I'm now going to quickly cover a little bit of off-syllabus stuff. We only have half an hour left, so I'm not going to get through all of it. If you are interested in it, this will serve as like an intro to convex Altric, and then if you're interested, you can learn in your own time. Obviously, this is not required for this course. It used to be on the course, which is why I've got the lecture slides here for it, but it's not on the course anymore. So feel free to tune out now. But for those students who are interested, here we go. So what are DP optimizations? Sometimes you're doing a DP, but it's too slow. You got a slow recurrence. So in other words, we have like order n states and order n recurrence. This is order n squared DP. Our DP is too slow, for example, in this case, because our recurrence is too slow. We can optimize this. One way is with range trees. We can use range trees to improve DP recurrences from order n to order log n. This lecture will show a few cases, actually only one in this lecture. The old course covered a few, but we'll cover just one. Given a well-structured recurrence, which I'll explain in more detail, how we can speed it up. This does not help if you've got too many states. If you remember, if when we're solving greed, the last problem, initially we had too many states. If you have too many states, the only way to improve is to get rid of states. These optimizations will not work. If you have enough states but too slow of a recurrence, this helps. Okay. Convex Hull trick. Of the optimizations, I chose to cover it today because it's the easiest to apply. There's a few of them. There's, if you're interested, there's the main ones. There's convex Hull trick. There's divide and conquer. It's different to divide and conquer you've heard of before. There's also notes, but this is very niche. Okay. This is useful when recurrence is formed by linear functions. I'll explain that in more detail in a minute. But once you get good at spotting these, more problems become linear functions than you first realize. You'd be surprised how often it pops up. Obviously not in this course, but in general. General setting is doing a 1D DP, for example. Let's say you're calculating dPn or increasing I. And let's say you've got an array M of size n. You can think of these as gradients of lines. I'm going to say this is in decreasing order. So our gradients are decreasing as I increases. You have an array Pn. These are, let's say, positions. Then let's say our dp looks like this. Base case dp0, and the recurrence is, for each dpi, it's the minimum of all j is less than I of dpj plus mj times pi. That is, for each j is less than I, it's dp value of j plus this function of j times this function of I. Again, it's not immediately obvious until you see problems as to how this helps. But once you know the trick, it becomes more obvious. But let's look at this. What are we trying to do? So there's an obvious order m squared solution. Just for each j, calculate this, find the minimum j. But what does this look like? This is a line, right? So this is your like y equals m x plus c. This is like your equation of a line. And so essentially, you're given a bunch of like lines defined by their slope and their intercept. You're given some x value, and the question is, of all your lines, given my x value, what is the minimum line along this x value? I'll give more examples to make it obvious why this is the case, but the idea is we're finding the minimum value out of these, and these are lines. So, for examples, let's say we have, so far we've found dp0 is -2, m0 is 2, and we found the rest of these. Yeah. Let's say we want to calculate dp3. And for now, let's say that p3, we're not going to say what this is yet. Then we have a line with slope 2, intercept -2, slope 1, intercept -1, slope -1, intercept 5. And the question depends on what p is. So let's like graph this. I've got a graph on the next slide. We have these lines. This is the same thing I said before. So dpi is a minimum of a set of lines at some x coordinate, where that x coordinate is whatever p3 is. As a side note, if I'm moving too fast, let me know and I can answer questions. Otherwise, I'll just keep going through this. So please stop me if I'm going too fast. This is kind of an advanced concept. So our three lines are 2x take 2, 2x take 2, x take 1, and -x plus 5. Let's graph them. First of all, let's talk about how to speed this up. Let's say we can speed up this DP. We're going to try and speed up the DP calculations rather than doing an order n. Because notice, whatever P3 is, that's our x coordinate. This one, for all of these lines, for a given x coordinate, what's the minimum y coordinate among all these lines at our given x coordinate? And the order n is trivial. I want to speed this up, do it faster than order n. And to speed this up, we're going to build a data structure. And that data structure supports some operations. Operation 1 is add a line. So we have our line y equals mx plus b. Using plus c, but plus b works as well. And we're going to add this. If we get to it, you'll see that we have the requirement that n is strictly less than all gradients so far. If you remember, in our arbitrary problem, we said that was the case. I'm not going to go to that too far back. But we can add a new line as long as its slope is the least so far. And a query which says, given some q, or some x coordinate, over all our lines, what is the minimum x or y coordinate? Now, hopefully you can see that if we can solve this, we're going to have this add function be amortized order 1, and this query function be amortized log. In that case, then we can solve the DP in order n log m because each query is order log m. Again, we haven't described how this data structure works. If we can do this, then we can solve the previous DP in order log n time because we just add the lines one by one as we calculate them, and at each point in time, just do the query. To get this, we need some observations regarding the set of lines we are querying. So just going to use our example from before. So we have m of I are the gradients and b of I are the y-intercepts. So from before we had b of 0 is -2 and m of 0 is 2. So we have 2x minus 2. We have x minus 1. We have negative x plus 5. Let's graph these. So here we have negative 2x minus 2. That's this here. The orange one. The green one is what? We have x take 1. It's not 2x take 2. Right, that's not how lines work. This is 2x take 2. I forget how lines work. This is 2x take 2. This one here is x take 1. And what have I done? And what's our last one? I have x take 1. No, I've still missed. What about lines? Sorry, I'm getting 2, 1, -1. This is negative x plus 5. Sorry, this is too confusing for me. Sorry, the lines here are x take 1, 2x take 2, negative x plus 5. Evidently, year 9 maths is too hard for me. These are our 3 lines from before. And the important thing is, our aim is to query the minimum x coordinate over these 3 lines at some given coordinate. And the question is, what could this be? Let's just emphasize the minimum. This black line here is the minimum x coordinate for some given the minimum y coordinate for some given x coordinate. So if x was 2, for example, the minimum y would be 1. If x was 4, minimum y also 1. X was 0, minimum y is -2. And let's look at this structure for a minute. What are the important observations? Well, one is the fact that it belongs to this line for a bit, the green line, and the blue line for a bit, then the orange line for a bit. Yeah, so importantly, the line with biggest slope, so the line with the most positive slope, as we go towards -infinity, is going to be the smallest one. Why? Because I consider the line with the biggest slope, sorry. As we go towards -infinity, at some point, it's going to overtake everything and become the smallest line. So we start with the line with the smallest slope, and at some point, biggest slope, sorry, and at some point, a line with decreased slope, so a line with less slope will overtake it. Because as x gets bigger, a big slope becomes a bad thing. So at some point, a line with a smaller slope is going to overtake us. And then at some point, a line with even smaller slope overtakes it. And as we go towards positive infinity, the dominating line is the one with the most negative slope, the smallest slope. Because as we go towards negative infinity, or positive infinity, sorry, we want a small slope. Another observation, if a line gets overtaken, it will never be the minimum again. Why is that? Because if I get overtaken by this, I think quite obviously by this diagram, I'm never going to be better than it again. Also, lines intersect. So, in other words, each line is only the best for some range of x coordinates from whenever it overtakes to whenever it gets overtaken. Also, these lines are in decreasing order of slope because, again, a line will only ever overtake a line if it has smaller slope, because consider the intersection of two lines. Before the intersection, the one with bigger slope wins, and after the intersection, the one with smaller slope wins. So yeah, we have these lines ordered by their slope, and they're each dominant some range. However, note some line like this might never be dominant. It is possible to have lines that are just are pointless. Like this line here, it doesn't help us at all. So we have some lines that are dominant for some range, and they're sorted by their slope, and the rest of the lines just don't impact it. On the next few slides, we go over those more formally. I thought the diagram is useful to kind of describe them. Key observations. This is the upper convex hull of the areas below the lines. That's just kind of math term for this. That's just math speak for this structure here. This means that each line is optimal for some continuous range of x, which is what I said before, possibly empty. In other words, some line might never help us. And yeah, as we move from left to right, the gradient of the optimal line never increases. That's because a line only ever gets overtaken by a less steep line. And what we do is we maintain this convex hull by maintaining the list of line segments that produce this convex hull. And the idea is, if we have these line segments, we can just binary search it. So if we know we have some x coordinate, we just binary search our line segments to find the one that we're optimal for. We then plug in our x coordinate to this formula, and we get our minimum answer. That is essentially what convex hull trick is. But for the next however much time we have, I'll explain some more detail. So yeah, we define a line as being dominant if it's a minimum. That's just the same as a line is dominant if it's on this black line here. So yeah, we store the lines that make up the convex hull in the order they appear, and the order they appear is decreasing gradient. Yeah, note some lines are never in the convex hull. And yeah, to calculate a range, we can just binary search. So we keep lines in a vector. So what that means is this code here finds the x coordinate of the intersection of two lines. It's pretty easy to rederive. I'm not going to do it, but like basic maths, you can rederive this. X coordinate intersection of two lines. We store the optimal lines in a vector, and we guarantee that the m's are in decreasing order. Then we can just binary search this vector to find the minimum coordinate. So we keep lines in a vector. As a recursive method, remember, we have to add a line. We have to query what's the line on the upper convex hull at x equals q, or equivalently, what's the minimum y coordinate? That's our first operation. And add a new line. Do this with binary search, as I said. We just binary search over our list of line segments to find, because we have this function to find the intersection, the binary search to say, we check this line here, right? We check the intersection of this line and the next line, and we go, okay, if our x coordinate is before this intersection, then that means we're on this line or before. If our x coordinate is after this intersection, then we binary search afterwards. That's how we binary search on hull. So yeah, this is just describing how the binary search works. Because we want to find this, as I just said, so we can binary search. I'm going faster to see how much we can get through. So like, I'm skipping through stuff that I don't think is necessary. But if you think it's necessary, let me know. Otherwise, I'm going to kind of go as fast as I can for the last 10 minutes without going too fast. So here's our code. Here's our query code. So it's binary searching. We're saying, okay, if the intersection of this line and the next line, if it's bigger than x, that means like the intersection is bigger than x. That means we're on this line or below. Otherwise, we're on this line or above. That's our binary search. Once we're done, we have the optimal line. We just get the slope of that line multiplied by our x coordinate plus the intercept of that line. That's our answer. Because remember, our query is actually asking what's the minimum function result. So we have to return it. This is a code for that. So adding a line, we use the fact that the slope is decreasing. So whenever we add a new line to our hull, we guarantee that its slope is the smallest so far. This guarantee is required for our data structure to be nice. If you add lines in any order, it becomes super messy. And luckily, in a lot of DP problems, this is enough. Okay, so remember that what I said before, if a line has the smallest gradient possible, that means that as we go towards positive infinity, this line will become optimal at some point. Because at some point, having the smallest slope will beat over, no matter how bad your intercept is, as you approach positive infinity, the slope's what matters, and so you'll be the dominant line. Which means you are optimal for some kind of suffix of the number line. So for some x coordinate and beyond, the new line you're adding is optimal. However, this may cause some lines to disappear from the convex hull. As an example, let's say we add this line to our earlier example. So we're adding this orange line here. Remember, our old convex hull was these three lines here. But our new convex hull in light blue, no, light blue is hard to see. In green, so nice green. In blue is this here. And notice that we can completely remove both this red line and this blue line from our convex hull. After inserting this orange line, the only two important lines are now the green line up to a certain point and the orange line up to a certain point. Now, one observation is we're always going to remove some like suffix of lines. By that I mean, we're going to remove like the last line and maybe the second to last line and maybe the third to last line. But we're not going to remove like the last line and the fifth to last line. And because if we consider the range of x coordinates that each line is optimal for, so we have like, originally we had green for a bit, and then we had blue for a bit, and then we had red for a bit. We add orange, and we see orange is optimal for this range here. That means, well, we delete red, we delete blue. Obviously, if we delete a line here, we must delete all lines after it because of the fact that the optimal values of this one go towards positive infinity. And that is because we add lines in decreasing gradient. The fact that this line has the smallest gradient is what makes this fact true, that we only ever delete like a prefix. This is what I said before. So yeah, useless lines are always at the end of the convex hull. So we just kind of keep popping lines off. Well, useless. How do we check if a line is useless? Well, let's just check. Well, what we do is we have a convex hull and consider on our convex hull. This is, oh, I don't want to change. I want to get on a convex hull. This is the second to last line. This is like line, second last line, and this is the last line here. If we're adding a new line, to work out if this line, the new line invalidates an old line, we check the intersection of these two lines here. That's here. We check the intersection of, that's here, sorry. We check the intersection of the two blue lines, that's here. Why is that? Well, that's the point at which this line becomes useful in the old convex hull. So we know from this point onwards, the second blue line is useful. However, we check the intersection of this line and this line, and see that, well, a new line is useful from here onwards, which means that it invalidates the old line. Does that make sense? So over here, we check the intersection of our new line and the old last line, and that's useless if that is less than the intersection of the last line and the old second to last line. Again, draw pictures if you're not sure about this. Just draw pictures and you'll see this is true. Again, yeah, if you're not sure, just draw pictures and it should be obvious. So how do we add a line? Well, we just go, while there's more than two lines on our hull, and while the line is invalid, just pop from back. So we just keep removing lines while they're not useful. That's how our line is. Amortize 1 per add, because each line gets removed at most once, and log per query. Yeah. So it's 9 p.m. now. I might very quickly discuss a problem that uses it very quickly. So like slides have stuff about like using ints and stuff. I'm gonna skip over that and very quickly go to a problem. And we'll probably discuss this quickly in 5 or 10 minutes, and then lecture's over. So in this problem, you have endpoints on a walkway, and in this case, there's like a walkway with endpoints. You want to cover all the points by placing lines over them. However, the cost of building a line is some fixed c plus the length of the line squared. So if like c is 10, and length of the line is 2, it costs 4 plus 10, 14 to build this line here. And the question is, what is the cheapest cost to cover everything? Notice it's not necessarily optimal to cover each thing with its own line, because if C is large, it's cheaper to like build a line between two things. But if 2 points are way spaced away, it's cheaper to have them on their own. That kind of makes sense. I'll go over the sample input to make that clearer. But you have up to 10 to the 6 points. The cost of building a line up 10 to the 6, you're given the points up to 10 to the 9. Let's just go over an example. So let's say we have points at positions 1, 2, and 10, and C equals 5. Cost of covering them all individually is 15, because length 0 here, length 0 here, length here, 5 each, 15. The cost of covering them all by one long range is 5 plus the length of the range squared, that's 10 minus 1, 9. So 81 plus 5, 86. If we cover 1 and 2 with one range, this costs 6, 5 plus 1. Cover 10 on its own, that costs 5. That costs 11. That's an impossible answer. That's a problem. So obvious n squared dp. The n squared dp is dpi is the minimum cost to cover the first I points. The recurrence is, for like case I, we're gonna consider how far along we build. We say for each j less than I, it's the cost of building this line segment here plus dp of j take 1. That's the rest, which is equal to the minimum of I is less than j of dp I take 1, that is the cost of covering everything else, plus the cost of building this line here, which is c, plus the distance squared. If you expand that, you get this. Focus on the last term here. That is, this looks like a relative function if you squint hard enough. We'll see how this fits into our framework. So we have this recurrence here. So I'm going super fast. I'll be done in the next 5 minutes. So we want to find recurrences that look like this. Notice that if we set mi to be negative 2xi and pj to be xj, then we have an equation of the form y equals like m times x, and c is just kind of everything left over that depends on I. So c is this plus this. And these two things here are constant of the query. So I think we can kind of finish here. The idea is we have the slope is this. The intercept is everything that depends on I. So our line is like C is this, M is this. Notice that this depends on J. This means this is like constant to the query. In other words, it doesn't matter what line we take, this is constant. This is our X coordinate. And this is pretty rushed. But if you want to read the rest, you can read the lecture slides. I've been talking for 3 hours, so I think maybe it's time you all take a break. And yeah, if you're interested, you can read the rest of the slides. But yeah, that's it for today. Of course, this is off syllabus, so read if you want. It's a cool trick. Okay, I guess thanks everyone for coming. Sorry I couldn't fit all of this, but I hope you kind of covered enough that you can read the rest up in your own time. If you Google convex hull trick, there's like plenty of stuff you can find to help you as well. There's like a WPEG article. This is the article that I learned convex hull trick from. Yeah, I learned convex hull trick from like this article here. So this might help you. Otherwise, you've got the lecture slides as well. But yeah, I'm going to stop the recording now.